So in this screencast, we're going to discuss a little bit about some of the abiotic factors that affect the variety and distribution of organisms in ecosystems. Particularly, we're going to look at aquatic biomes here. So learning objectives 2.9 and 2.22, 2.23, 2.24. You can look at those. So aquatic biomes will cover most of the Earth's surface, as you see here, but there are, of course, varieties within that due to the physical geography of the Earth's crust. You have shallow areas, for example, around the Caribbean basin, but then you also have extreme deep water basins here, for example, off the western coast of South America. So those are all marine environments, and then of course inland you have the great freshwater biome surrounding the Amazon River, for example, as well as the Mississippi River here. So we're going to just take a quick look at some of these different biomes. One of the main abiotic factors affecting diversity, distribution, and abundance of organisms is the salinity, the concentration of salt in that water. This image here shows you from the most concentrated, we would call that a brine. The unit is in ppt, or parts per thousand, which is the traditional way of representing the salinity. So this is extremely salt water on one end, and at the other end, the other extreme, you have fresh water with less than 0.1 ppt salt. So then you have, of course, a range of that salt. Right? The saltier waters, we refer to them as saline. Right? Saline. Brackish waters are a mixture of somewhere between the saline and then the fresh water. So on the left side of this diagram, you see, for example, that the Red Sea is around 40 parts per trillion, and then you have drinking water down here, right, 0.1 part per trillion. So the freshwater ecosystems have life that has been adapted for surviving in freshwater. Then you have situations like here where you're getting not really fresh water, but not really super brackish water, but that the limit of that salt on agriculture, right, so growing crops and things, that salinity line is right there. Everything above this, right, a little bit more salt water. So here you're having in this where the fresh water meets the ocean water, right, you of course have your estuaries. Right. For example, right, we live near one of the world's most famous estuaries, the Chesapeake Bay. The average seawater then here is about 34.7 parts per trillion. And again, that is going to affect which kind of organisms survive in those waters. Other abiotic factors, one that we've been discussing in class, is light. And here we see a graphic that demonstrates that in bodies of water, you have the first few meters of that water here is known as the photic zone. Right? And of course, this is the depth that light can or will penetrate. And the closer to the shore, you will see organisms that are adapted for that, and we refer to these sometimes as SAVs, or submerged aquatic vegetation. And these SAVs are critical to increasing the dissolved oxygen content of that water. So near the shores and in these photic zones, you see lots and lots of photosynthesis happening. Right? Not only the SAVs, but also in this photic zone, you're going to have your phytoplankton that are harnessing that light energy, right, and driving photosynthesis. So the photic zone is one of the areas that I want to highlight. The other area that I like to highlight here is the benthic zone. So the benthic zone is at the bottom. and there is very little light here, right? Little to no light at the benthic zone, and this is where your detritivores were gonna hang out. Detrito. And of course, those detritivores are going to be decomposing any dead organic materials, as discussed in a previous screencast, and returning some of those nutrients back into the soil and back into the water. Right? So in freshwater ecosystems, we have this photic zone, this benthic zone. Right? The open part of the lake or the pond here would be referred to as the limnetic zone. So this is the open area sort of away from the shore, and then the littoral zone is closer to the shore. So just defining these physical boundaries, which then may influence or most likely influence the distribution and abundance of organisms. When we move to marine environments, we see very much the same situation going on here. We want to highlight this photic zone right here, again, which is where the phytoplankton are going to be hanging out. The other area, of course, that we highlighted before, the benthic zone exists here as well, right? But a lot of times these are even deeper, right, than what you would have in a freshwater ecosystem, so we refer to them as the abyssal zone. These are very, very extremely deep regions here. Right? Of course, these benthic zones and these abyssal zones are, of course, aphotic. Right? An interesting feature of deepwater marine systems are these vents, where magma is being, essentially it's an undersea volcano, right? So the deep sea vents, right? And you have extreme temperature here and extreme pressure here, and these areas are sites of nutrients and inorganic materials that are coming up that are being recycled up out of the Earth's crust. So these are also areas of interesting life forms that live down there, and some of the earliest life forms, some very primitive life forms on the planet, were believed to possibly have evolved down here at these deep sea hydrothermal, is the other term that they sometimes use, hydrothermal vents. Right? But that can be a source of nutrients as well. So what we see here is that a lot of these nutrients will be recycled by detritivores or will be put back into the benthic zone area. So then what happens, especially in freshwater ecosystems, a way that those nutrients get recycled back around is simply because the temperature is going to change it, especially in a temperate zones. Here where we are now about to enter here in Northern Virginia, autumn, where all summer long, this has been going on in our lakes like Lake Braddock across the street and Burke Lake, etc., where the surface waters are being heated up and creating what's known as a thermocline here. So the waters up here are warmer, right, cooler, and then colder down here. And this colder water has more density, so it will then sink to the bottom. Now in the fall, what's happening is that these surface waters that all summer long were heating up will now begin to cool, and as these waters cool, they become more dense and will sink down. And as they do, that creates a churning motion here, right, that will bring nutrients back to the surface. Now these nutrients that come to the surface, right, will then feed phytoplankton, right, and help them to give them a source of their inorganic materials to run more organic processes, to run photosynthesis, etc. So this is in the fall, but the problem is that of course the days are getting shorter here. So the light is getting, there's less light, days are getting shorter, and then we enter the winter where there is very short periods of light. The photo period is shorter. So there's short photo period, sort of limits photosynthesis. It limits photosynthesis. And then the temperature, again, is also playing a role here, where the surface temperatures are cooling, right? And you get this stratification again, right? Now the problem is, not the problem, but the interesting thing about water is that as it cools, its density gets more, and then as it approaches 0, the density changes again. So you have this ice layer forming here, right? And then you have a cooler, more dense layer underneath it. So your ponds and lakes and things typically do not freeze solid, at least in the deeper areas. So any of the fish and things that are surviving in here, right, they don't get frozen into like little fish sickle. As the photo period gets longer, right, longer days, you have more radiant energy, more radiant heat coming in. That, of course, is going to melt the ice. That melting ice brings the density back down a little bit, and that temperature and density change will again create a circling here, a cycling of the nutrients, and upwelling occurs of nutrients, and then the temperature is relatively uniform. You get nutrients there, and phytoplankton again able to survive and flourish photosynthetically when you come back to the summer time down here where the photoperiods are longer. So before we move on to the next slide, we just want to point out graphically what this looks like. So this was visually what it looks like here, 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 and here. But what we're doing over here with this graph is it's a little bit odd because your axes are sort of flipped here a little bit. But what we're doing is we are measuring the oxygen, right, concentration, O2, in milligrams per liter, which also is parts per million, right? And then the depth of the lake. So we're measuring the parts per million as a function of depth here in the lake. So the deeper we go, the less oxygen there is. And then the higher up we go, the more oxygen concentration there is. So a question might be, why? Why does this curve look like this in the summer? Another question over here, and again in depth, right? As we get deeper, the milligrams of oxygen, right, is high, right, but then remains basically pretty steady, right, all throughout, no matter what depth you have. A question would be, why does that make sense? Can you explain that from a abiotic and a biotic perspective? Up here in the winter, right, again, you're analyzing as you go deeper. The concentration of oxygen here is relatively high, and it sort of plateaus and then is going to drop off significantly. So again, the question might be why. And then again, over here in the spring, your graph looks like the one it does in the fall, and the question might be why. So freshwater biomes, just to wrap this up, freshwater biomes include your lakes, rivers, and streams. They're one of the main abiotic factors affecting life there is going to be the concentration of salt. And so the freshwater systems have very little salt concentrations in them. Right? Your estuaries, they're going to mark the boundary between freshwater and marine biomes. So essentially where the ocean is meeting the ocean meets the river meets the ocean. And again, we live very near to one of the most famous estuaries, the Chesapeake Bay System. And that system, the salinity of that water is going to change depending on how much rain is coming from upstream. So if we just take a quick look here at the Chesapeake Bay, here we are in Washington, D.C. area. Here's the Chesapeake Bay. The main tributary of the Chesapeake Bay, one of the main tributaries, of course, is the Potomac, but the real big one is the Susquehanna River, which is going to come out of Pennsylvania, right, and New York. This Chesapeake Bay watershed boundary line. So any rain that's going to fall on the land here, right, rain or snow, right, is going to eventually drain right here into the Chesapeake Bay. So if there's an extremely large amount of rainfall, this summer's been a relatively wet summer, so much more fresh water draining into the bay, so you have fresh water pushing out this way. Perhaps the salinity of the bay is not as high as maybe it might be in a really extreme dry year. In an extreme dry summer or season, you might have some of the ocean water pushing up into the bay, and therefore the salinity is going to change, right? And sometimes this happens extremely, and the organisms that are adapted for living in brackish water, if it gets outside of that salt range, they have a problem. They have an issue there. Right? So just a little bit there about some aquatic biomes. Right? If you have any questions, jot them down, bring them to class.